Hello everyone. In the previous video we have built the clock circuit for our 8-bit SAP computer, or simple as possible version number 1 computer. Here it is. In this video we are going to build the program counter. Ultimately we will build all of those one by one, so let's make program counter now. Now the program counter that's given by the SAP architecture is 4 bits wide, which means it can count up to the number 15 maximum. So it can have 16 different values from 0 minimum up to 15 maximum. Let's build it on Logisim. To add a new circuit, just like what we did in the previous video for the clock, we can hit this plus button and let's call it program counter. Now here we have a new page or a new circuit for the program counter. Now we can build it from scratch, like using D flip-flops and similar circuits. But the purpose of this video series is not to make those components, those registers and other things. I am planning to show you how to combine those things to make a CPU, not to make those things. Of course we can do them, but we are not going to do it. So instead of building it from scratch, we actually have a built-in counter. If we go to the memory section, we can see something called the counter. Let's bring it here. Now the first thing that we should notice is it's an 8-bit counter, as we can see from these data bits. Now the SAP computer requires only 4 bits wide, but it's okay, it doesn't hurt to use 8 bits wide. It is going to be fully compatible with this anyways, so we will keep it like that. The number that we see here is the current value stored in the counter, so that we can just look at it and know the value. As for the input and output pins, there are 7 pins, 3 on the left, 2 on the right, and 2 on the bottom. Let's see what they are. So here it says output, current value of counter. Okay, this is output pin. Let's bring an output like so. We immediately see some kind of error, incompatible with, and that's because this counter gives 8-bit values, and the pin that I brought over here, this pin has 1-bit output. So in order to make it compatible, we have to use 8 pins. Now we can see the content of the counter over here. Let's actually give it a label called value. The next pin is carry. It says carry is 1 when value reaches maximum. Now we are not going to need this output at all, so let's not even do anything with it. This is clear. When 1, it resets to 0 asynchronously. We definitely need to include this. It's north. So reset. Level location east. This is clock. Value may update. It doesn't mean it will always increment. This counter is capable of doing some other stuff, which we will see shortly. So let's just call it clock. Here we have count. Let's call it count enable. Data value to load into counter. So sometimes we do want to load the value of the current counter from different section of the CPU. This way we can easily jump to another instruction by just loading the value that we want our instruction to go or to point. Yes. Again, it is an 8-bit input, so we have to make the 8-pin input. This one input pin 8-bit, and let's call it data in. We have last and we have one remaining, and this is load. What? Okay, south it is. So let's call it J or jump. You will see what it does. Now, in order to toggle the values of the pins, we have to hit here. Now we can change everything. So first thing is first, let's toggle the clock and see what happens at the value of the counter. So nothing interesting is happening. Maybe we need to set some of these pins to 1. So let's actually hit count enable and see what happens to the value of the clock upon transitioning from 0 to 1. Okay, now if we see here or here, it is counting upwards. So it's incrementing. That's what we exactly want to do. If we want the counter to increment, we just have to enable count enable as 1 and jump as 0. Okay, let's also check the reset button. It resets it asynchronously to 0, regardless of what these inputs are. If reset is 1, boom, the value of value becomes 0, regardless of whatever happens on this side. Okay, let's make it 0 so that we can continue to experiment with the other input values. The next thing that I want to try is count enable 0, jump 1. If we transition clock from 0 to 1, we can see the content of data in is being latched to the counter value. So this way we can enable jumping from one address location to another address location. So 1, 0 means jump. The last thing that we haven't mentioned is when both of them are 1. In that case, it's actually decrementing if we see it. So we don't need this kind of feature in our CPU. I have never seen any CPU that executes instruction by decrementing the instruction pointer or the program counter. So we don't need to use this feature at all. So in summary, count enable 1, jump 0 should increment the counter. Count enable 0, jump 1. This should latch whatever the value of data in to the data out, like so. And this decrements it, but it's useless. And finally, we have the reset, which just sets it to 0. So that's it. Now let's test our program counter circuit from other subcircuits. For example, from main. This is the clock. We don't need to use it. Okay, let's even remove it. Let's bring program counter by clicking on it and click here. Okay, what are those inputs? We don't know what these are. We cannot be sure. So let's go back to the program counter and edit the circuit appearance, how it look like when we try to use it from another circuits. To do that, we click here and let's give it a rectangular shape by hitting here. 10 by 10. Now let's click on them, and on the bottom right we can see what this pin is. This is clearly the data pin that I set earlier. Let's give it a label, data in. Okay, let's also write all of the labels here one by one. Count enable, there was also just value, the current value. There was also clock. There was also reset. Okay, let's put them now. This is the jump. This is count enable. This is clock. Reset. Okay, this is data in. I forgot to bring this here. And this is the output value, the counter. And finally, the orientation pin. Let's remove this. Let's also change the border to 2. And yeah, it looked like our counter is completed. One last thing, let's put a big label over here. Let's call it PC, which stands for program counter. Let's make it bold and a little bit bigger. Maybe 36. Yeah. Now to test this PC, let's go to main and feed some input to it. Okay, let's start. Clock. Nothing happens because none of the inputs are set. Now let's enable count enable, and it's incrementing. Let's hit jump. The value of the input should be stored at the output as expected. And finally, when both of them are 1, it decrements we hit reset, it becomes 0. So this is how we exactly want our clock to work. If we look at Ben Eater's program counter, he is using another input called program counter out, this CO. We also need it, but I don't want to bring it now. We will talk about it later on the video series. So we will actually come back to modify this PC or program counter later on, because we have to deal with multiple outputs first, and I don't want to bring it now. Anyway, with that being said, the program counter of the SAP computer is now completed. It's 8-bit, unlike 4 bits that is used in the book. But like I said, it's fine. It's going to be backward compatible with this and even with Ben Eater's computer. So yeah, this is the end of the video. The next video is going to be about one of these registers, probably the A register or the accumulator. So I will see you in that video. So thanks for watching. If you have any questions, let me know in the comment section, or if I made any mistakes, or if you have suggestions, please let me know. Thank you.